Okay, great. So let's get started, and we will look at encryption schemes today. I hope you can hear me well. So we will mainly look at secret key or symmetric key encryption schemes, and in some sense we have already done that before. We have been through the one-time pad, and we have been through many of the classical ciphers. But of course, the classical ciphers could be broken, and the problem with one-time pad is that it had its limitations, right? So the key had to be at least as long as the size of the message, and the key could not be used, and so on. So today we will try to design provably secure symmetric key encryption schemes which do not have any of these problems. Okay, so let's try to recall first what was the definition of symmetric key encryption schemes. And we saw the definition of perfect security, which is something which we will not want to work with. We will try to come up with a computational definition. So let's get started with that first. So symmetric key encryption, or also it's also known as private key encryption. It's the same thing. Symmetric key encryption, let's call it SKE. So any symmetric key encryption scheme must specify 3 different algorithms, as you can expect. The first one is the key generation algorithm, which sort of takes the security parameter as input and outputs the secret key K, right? So the security parameter in some sense will determine the length of your secret key. And in many schemes, the secret key might be just a random number. In other schemes, it might be chosen in a more sophisticated way. Then we have our encryption algorithm, which takes the key, takes the message, and it's supposed to output the ciphertext C. And then we have the decryption algorithm, which takes the key, the same key, and the ciphertext, and it outputs some message. Let's call it M prime. Okay. So this is just the syntax. And when do we call a symmetric key encryption scheme to be a good symmetric key encryption scheme? So there are 2 properties. First is correctness. So correctness specifies what happens when there is no adversary, right? So in that case, as you would expect, if you did the key generation properly, if you encrypt it properly, and you decrypt it properly, then M prime and M should be the same, right? You should get back the same message. So here we want to say the following. Correctness property is what you would expect. The probability that the decryption algorithm on K and C gives you the message M such that K is generated properly and C is the encryption of the message M under K. This probability should be 1. So correctness must always hold. And now what about secrecy, or what about privacy? So it will be a very straightforward generalization of perfect security, which we have already seen. So perfect security talks about 2 distributions being identical, and here we will just change the 2 distributions to being computationally indistinguishable. So let's try to recall perfect secrecy. So what is perfect secrecy? It must be the case that for every pair of messages M0 and M1, for every ciphertext C, probability that you encrypt the message M0 and you get C such that K is generated properly. This probability should be exactly the same as the probability of getting C when you start with M1 instead of M. And again, this is the same, right? And now what I want to do is I want to just make a slight change to this definition. So recall that we saw Shannon's theorem earlier, which showed that any scheme which is perfectly secure, which has perfect secrecy, can actually be broken if the key size is smaller than the message size, right? So how do we overcome this? And in some sense, the proof of the Shannon's theorem already gave us a hint. In Shannon's theorem, we construct an adversary which sort of goes through every possible key. So the adversary is bounded, and we would like to work with computationally. So the adversary is unbounded, sorry, in Shannon's theorem. And we would like to work with computationally bounded adversaries, and we would like to overcome this limitation. Okay, so essentially here we were saying that these two ciphertexts sort of look identical completely. So let's try to generalize this, and this will give us what is known as indistinguishability based security. And note that this is not the only definition of security for symmetric key encryption, but probably one of the most natural, if not the most natural. So indistinguishability based security, or let's just call it indistinguishability security. What we need is that for every pair of messages M0 and M1, the distribution of ciphertexts starting with M0 should look computationally indistinguishable from the distribution when we start with M1, right? So on the left side, we have encryption of M0, and a key is generated properly. That always goes without saying. So this is computationally indistinguishable from the ciphertext produced by M1, and again the key is generated properly, right? So what this says is that when an adversary looks at two different ciphertexts having message M0 or M1, adversary cannot even tell them apart, right? So this is mostly the definition which we will work with. Why is this the right definition? So again, when we considered computational indistinguishability, we also considered the prediction indistinguishability, or the prediction probability based definition. We can try to do the same thing here, and we will see that these notions are actually equivalent. So let me try to define another definition, indistinguishability security, and let me just call it an alternative definition. You could probably have also called it prediction indistinguishability, but in cryptography, we typically just refer to it as indistinguishability security, an alternative formulation. So here what we need is, again, for every M0 and M1, for every PPT adversary A, we will choose one of these two messages at random, and we will ask the adversary to predict which one we chose. An adversary should not be able to succeed with probability noticeably more than half. Okay, so probability that adversary gets the ciphertext C and adversary is able to output a guess for the bit B such that key is generated properly. Next, you choose B at random, which basically selects the message that you encrypt. And then finally, your ciphertext is an encryption under K of the message MB. And what we need is this probability should be very close to half. Right? So this is a very natural definition. And by the way, an interesting thing to note in this definition is, why do we only consider two messages? Right? Your message could be very long. There could be many different possibilities of the message and so on. So the nice thing about just considering two different messages is that essentially you can think of it as giving a lot of information about the message to the adversary. So suppose your message is very long, right? Suppose we even give the adversary all the bits except a single bit of the message, right? Given this information in adversary's head, there are only two possibilities for the message. Adversary already knows all the bits. Then the remaining bit could either be 0 or 1. Then we call these messages M0 or M1, right? And even at that point, adversary cannot determine this last remaining bit of the message. And instead of a bit of the message, it could be any arbitrary predicate of the message, like XOR of all the bits or something like that, right? So yeah, so here we are really saying the following. The security of the encryption scheme does not depend on the message being private. Okay, it only depends on the key being private. Even if adversary knows most of the message, still the remaining information, it's hidden in some sense.
So the one thing that's sort of counterintuitive here is that this definition seems to be trying to prove, like, if we have messages and we don't know the key, we won't know what they encrypt to. Whereas it feels like what we'd want for security is, like, if we had ciphertext and we don't know the key, we can't figure out what the original message was. And so does this direction just like imply the inverse as well, or?
No, in fact, if you look at the second definition, adversary is actually given the ciphertext, right? Adversary has to guess the message.
Well, but we generate the ciphertext as like one of these two things. And so it's really guessing, does this thing encrypt to a given ciphertext, not does this ciphertext decrypt to?
Yeah, so the only thing we require is that you generate the key properly and you generate the ciphertext properly. Ciphertext should be one of these two messages. And then adversary sees the ciphertext, right? Adversary sees the ciphertext and the goal of the adversary is to guess the message.
Okay.
And maybe what you're saying is might be more true for this definition because, but even in this definition, right, you see like two different ciphertexts and, or rather you see one ciphertext and you have to guess which message it is coming from.
Okay.
Any other questions? All right, so let's very quickly, let's try to prove that these two definitions are equivalent before we move on. And the proof is like very similar to the proof of computational indistinguishability and prediction indistinguishability being equivalent. We saw that they were equivalent up to a factor of 2, and that's exactly what we will end up getting here. Okay, so let me try to see if I can fit the proof here. So the statement is indistinguishability security implies indistinguishability security alternate definition and vice versa. I'm just inventing my own notation here. So how are we going to do it? So let's, okay, let me just use this part. So again, we will just do one direction and the other direction is just sort of doing all the steps in the reverse order. So suppose that say indistinguishability security holds. Okay, so you are given that your scheme satisfies this definition, and we want to prove that this implies that scheme must also satisfy this alternative definition. So if the indistinguishability security holds, let's try to see compute indistinguishability security alternative equation, for lack of a better word. So we are looking at this definition, and we will try to sort of compute this one. Okay, so first, if indistinguishability security holds, what does this mean? This means the following: the probability that A gets access to C and outputs 0, such that K is chosen from the key space and C comes from encryption of K of M0. This probability minus probability that A of C equals 0. Same thing, except now we are encrypting M1. So this is negligible, right? So I'm just taking this equation. Sorry, not this. This equation. And I'm expanding it. Right? So if indistinguishability security holds, then the probability of A outputting 0 on these two different ciphertext distributions cannot be very different, negligibly close. So what we will do is we will call this P, and we will call this P prime. Okay, and this means that P and P prime are very close to each other. Now let's go to the alternative definition, and let's just try to express it in terms of P and P prime.
Sure.
Yeah.
Isn't this the the IS and ISA the same thing as prediction indistinguishability and computational indistinguishability proof that we did last class?
Yeah, I already said that.
Okay, sorry.
Okay, so now maybe I don't even need to do it in a lot of detail. So now we are looking at probability of AC equals P, such that K is generated properly and B is generated at random, and C is generated by encrypting K and MB. So we want to compute this minus half. And now we can divide this into two parts, right? Part 1 is when B was 0, part 2 is when B was 1. So this is the probability that AC equals 0 and K is sampled from keygen and C is encryption of K comma M0 into probability that B is half. So this is just half plus now we are looking at probability that AC equals 1 and you encrypted 1 into half minus half. That's what we are interested in. So note that this is, what is this? This is exactly half, this is exactly P. P times half plus what is that? This is 1 minus P prime times half minus half. Okay, and then in some sense, this is P by 2 minus P prime by 2, and that is of course negligible if P and P prime, they are negligibly close to each other. Okay, any questions? So now let's move on to actually building symmetric key encryption. So I already hinted in the previous classes how we might be able to do that. So the first construction will just follow from a PRG, and it will give us one-time security. But it would still be better than one-time pad in the sense that you can encrypt messages which are longer than the key. Okay, so one-time encryption using PRG. So here we will start with a PRG. Let's call it, you are given a PRG. So how does key generation work? So you just sample a key, and let me actually specify the input size of the PRG. So it takes an n-bit seed and it stretches into L of n-bit output. And we will assume that your message space is M is coming from 0, 1 to L of n. So how do you sample the key? Key is just a random string of length n, because this is what our PRG will need later on. How do you encrypt? Using this key. Your ciphertext is simply M XOR PRG of K. Okay, we are just using one-time pad, except that now we are first stretching our key to the required size by an application of PRG. And if our PRG is any good, then the output of the PRG still looks uniform, which is what the one-time pad needs. How do you decrypt the ciphertext? You output C XOR PRG of K. Okay, correctness is obvious. If you do everything properly, then you get back the same message. which you started with or which you encrypted. And let's try to prove the security. Okay, so we'll try to prove indistinguishability security. And to do that, what do we need? We need the following. For every M0 and M1, we need to show the following: M0 XOR PRG of K such that K is uniform, is computationally indistinguishable from M1 XOR PRG of K, where K is uniform, right? This is the ciphertext when you start with M0. This is the ciphertext when you start with M1. You need to prove that these two ciphertext distributions look computationally indistinguishable, right? And again, we will just use a hybrid argument. This proof is, completely straightforward. So our hybrid 0 will be M0 XOR PRGK. K is uniform. Hybrid 1 is M0 XOR, let's call it uniform distribution on L and L. Okay. And again, I'm not doing the proof in great detail, but here the point is that if the key was generated at uniform, then the guarantee that the PRG gives you is that the output of the PRG looks uniform, right? If somebody can distinguish H0 and H1, some PPT adversary, then you can construct another PPT adversary which can distinguish the output of the PRG from uniform. Okay, so this follows. H2 is if I take a uniform string, I can XOR anything with it. The result is also a uniform string. Okay, and you can try to prove it by looking at any specific string, and you can try to verify that the probability that you arrive at that string here as well as here is just 2 to the power minus L of n. Okay, so this hybrid and hybrid 2, they are actually equal distributions. There's no cryptography involved. I am not even talking about computational indistinguishability. On the other hand, hybrid 0 is computationally indistinguishable from hybrid 1. And here we have exact equality. It's typically written with this sign. Okay. And then you go to hybrid 3, which is M1 XOR UFLN. Right. So starting with H2, now we start going in the reverse direction, except instead of M0, we are talking about M1 here. Hybrid 4 is M1 XOR the PRG of K. K is uniform. And then we are done. End of the proof. Okay, any questions? Does this make sense? can you go from H1 to H3 directly? H1 to H3, yeah, actually you can do that. In fact, you don't even need any hybrids after H2, right? Another argument which you can write is that M1 is computationally indistinguishable. Sorry, you can say H0 and H2 are computationally indistinguishable, right? And in the same way, we can show that starting with M1, again, we can arrive at H2. And then by transitivity, you can go from M0 to M1. Okay, so what this means is now, given a PRG, we have been able to overcome the limitation of one-time pad. Now our key can be small, like just n bits, and you can encrypt arbitrarily long messages, right? Now the question is, this is still one time. That's the main remaining limitation of this this scheme. So what do we do about that, right? We would like to go to schemes where we can encrypt multiple messages even, right? So one option is to keep a counter. And note that in the counter idea, I talked about it a little bit last time, you have to change the definition of encryption scheme, right? So to show you the definition, again, an encryption scheme only takes the key and the message as input, right? It doesn't take as input any counter or any other type of state, right? So counter idea is extend the definition to allow for a counter CTR as input to encryption and decryption algorithms. Let me not write the full definition again. And then basically what does our scheme look like? Key generation remains the same. Encryption takes as input the key, the counter CTR, and a message. Okay. And then you output M XOR bits of PRGK starting from position CTR plus 1. So that is your ciphertext. And then your CTR becomes the older counter plus length of the message. Okay. Now, yeah, and the decryption will also take the counter. The decryptor will also keep maintaining the same counter, right? So there are two problems here. So one is the problem of synchronization. So first, what if there are multiple encryptors? So that's question number one, right? If there are multiple encryptors, you need to make sure that your counter, the same counter, is not used more than once, right? And in distributed computing, keeping a synchronized value across multiple different machines, it's a notoriously hard problem. Another question is efficiency as we go on. So note that after, let's say you have encrypted 1 million messages, then what you need to do is when you want to encrypt the next message, right? You need to apply the PRG. You need to keep expanding the output until you reach like the millionth plus 1 bit. Okay. So as you encrypt more and more, as your system gets older and older, it becomes more and more efficient, more and more inefficient, right? Because you need to continue evaluating the PRG and continue stretching the output until you actually get to a place which you have not used before. So yeah, so this is a simple idea, but we would like to do better. And we will try to do better using a PRF. So our goal would be, using a PRF, we would try to construct an encryption scheme which is secure for encrypting multiple messages, right? But our definition so far only talks about encrypting a single message. So our first goal will be to first define what it means for an encryption scheme to be secure for encrypting multiple messages. Okay, and this is known as multi-message encryption. Let's swap out the board. Okay, yeah, so looking at this plain old definition, you encrypt once, you decrypt once, and then you start talking about security and so on. So that's not what we want. So in multi-message security, you encrypt a set or a vector of messages. So now you have, for every pair of message vectors. Okay, so let's denote these by M0 I, where I goes from 1 to, let's say, Q of n. Here Q is a polynomial. And then you can choose a completely different set of messages. Okay, and by the way, the length of the messages should be the same. So for all I, M0I length must be the same as M1I length. What do we need? Experiment 1, I encrypt everything from this set, from the first set. Experiment 2, I encrypt everything from this set, right? So I obtain a bunch of ciphertexts in experiment 1 and experiment 2, and what I want is that given all of these ciphertexts together, an adversary cannot tell whether we started with the first vector or the second vector. So looking at the distribution, encryption under the key K of M0I, okay, for all I. and K is coming from key generation. So this is a bunch of ciphertexts. And what I need is that this should be computationally indistinguishable from all the ciphertexts are included in the distribution, right? Does this make sense? Any questions?
Sir, I had a small question. Maybe I missed this, but like, why are QN dash and QN, like, why are they not same?
Oh, it's a comma, not.
Oh, okay. Sorry.
Yeah, it's the same. It can be any polynomial number of messages. Okay, so before we try to construct encryption schemes which can provide security against this type of definition, let me make a very important point which you should always keep in mind, and that's the importance of randomization in encryption schemes. Okay, so in cryptography you will see that almost all the encryption schemes which we use in practice, they are randomized. What this means is that the encryption algorithm generates some sort of random number and uses that to generate the ciphertext, and we will see why that is the case. So here is a theorem which says that any symmetric key encryption with multi-message security must be either randomized or stateless. Sorry, stateful. Okay, stateful we have already seen by keeping a counter how we can construct a multi-message encryption scheme. But we don't really want to go to stateful encryption schemes because of the problems which I talked about. So then this theorem is saying that essentially we have to go to randomized encryption schemes. So proof of this is actually very simple. Consider two different message vectors. So this is vector 1 versus, let's say, M1, M2, where M1 is different from M2. Okay. Now observe that if you encrypt M0 twice, if your encryption scheme is deterministic and stateless, you get the same ciphertext. Okay, so what is the input to the encryption algorithm? Input is the key and input is the message, right? If you encrypt M0 twice, you are doing it under the same key. Then key is the same, M0 is the same, message is the same. There's no randomness involved in encryption. There's no counter involved in encryption. So the output must remain the same. Any deterministic and stateless encryption scheme has the disadvantage that when you encrypt the same message, you get the same ciphertext, right? So here you will end up getting something like C0, C0. Here, if you're encrypting two different messages, then the ciphertext must be different. This follows from the correctness property. Then you get C1 and C2. Okay. And can you distinguish between this and this? Of course you can, just by comparing if the two strings are the same or different. Right? So this is not by any means computationally indistinguishable. Okay, so such type of schemes cannot satisfy multi-message security. Any questions? So now how can we satisfy is that IND-CCA? No. A CCA security is a more advanced definition, which we will not look at. It's IND-CPA. Okay, so let's try to construct then multi-message encryption schemes, and we will try to use a PRF. So you are given a PRF. Let's just denote it by PRF. This takes as input an n-bit seed, and then another index of m1 bits, and then it gives you an m2 bit output, and our messages which we want to encrypt will have this length m2, right? So so how does this work? Key generation is just sample uniform string of n bits. Okay, encryption. Now encryption is randomized. Okay, so what you do is you first sample a random string of m1 bits, and then you output your ciphertext. See, your ciphertext will now have two different components. First is this random number, or the index is given in clear in the ciphertext. Next, you evaluate the PRF on the secret key and this random index, and you XOR it with the message. And let's also denote it by C1, or let's say C0 and C1. So there are two different components in the ciphertext. How do you decrypt the given ciphertext? Again, very natural. As part of the ciphertext, you have the index, right? You have the PRF key. So you evaluate the PRF, and then you just XOR it with C1, and then you get back your original message. Okay, so you output, so C equals C0 and C1, you output simply C1 XOR the PRF output on K and C0. Now, the interesting thing about this encryption scheme is that even if I encrypt the same message multiple times, I'm very likely to get different ciphertext just because this random number is sampled uniformly every time. And very likely it will continue to be different. Okay, and again, correctness is straightforward here. Let's try to prove security. And as you can expect, while proving security, we will try to rely on the fact that the PRF output is indistinguishable from uniform, and hence this is also essentially like a one-time pad. So let's try to construct several different hybrids. And again, keep in mind that we are encrypting multiple messages, not just one in the security game. So hybrid 0 is just our initial distribution. So keep this equation in mind. We have two different message vectors. We are trying to prove that this will be our H0 and this will be our last hybrid. And we will try to prove the indistinguishability between these two hybrids. So H0 is just this. Which is that you are given, let's call it Ri, comma, M0I XOR PRF on K and Ri. And here Ri is chosen at random M1. Okay, so this is and key is generated. Uniformly from 0, 1 to the power n. Okay, so this is our starting ciphertext distribution. Right? For each message, let's call it M0I. I generate I sample a random number Ri. And the output consists of Ri in clear and then M0I XOR the PRF output on this random number Ri. Now, our first step would be to replace this PRF by a purely random function. Okay, and then we will try to rely on the PRF security in this hybrid. So Ri M0I XOR Random function is denoted by just RF. And there's no key here. Right? And now our claim is that these two distributions are computationally indistinguishable. Okay. The proof, it essentially follows from the definition of PRF and the fact that PRF and RFs, they cannot be distinguished. So suppose, again, let's do it in a little more detail by contradiction. So say you are given a PPT adversary A, which can actually distinguish H0 and H1. What this means is that this PPT adversary takes a sample from either H0 or from H1 and then can tell apart these samples in some sense. Then we will build another PPT adversary B, which can break the security of the PRF more precisely, which can win the guessing game. So the security of the PRF, I will remind you, with probability half plus noticeable of n. So how is the security of PRF defined? So you have a challenger and you have an adversary. So here our adversary B can make several queries. All these queries are either answered by computing the PRF or by the random function, right? And if our adversary can guess with probability better than half which one it is, then we win the guessing game. Okay. So how does B work? So note that B has M0 I's all inbuilt inside. Okay. And then for every I, B samples are I, and queries the challenger. On this Ri. And then uses the response. Let's call the response capital, should be superscript. Let's call the response capital Ri. To construct all the ciphertexts, right? So if the challenger was responding with a PRF, then the ciphertext distribution is exactly from H0. If the challenger was responding with a random function, then your ciphertext distribution is exactly H1. Okay. So now if the PPT adversary A can tell apart these two ciphertext distributions, then B can tell apart if it was a PRF or it was a RF. And B wins the guessing game with probability better than half. Okay, so this claim holds.
Sir,
Any questions?
yeah, so one question.
Yeah.
So for B, right, when it samples a bit 0 or 1, right, and like it will either get a random thing or something from the ciphertext. But like H0 has all of the things from the ciphertext, and H1 has all the things from the random thing. But what B will get is like, say, first 2 from the ciphertext, the next 3 from the random. So how will our adversary A can distinguish, like if you give it 10?
No. So recall the definition of PRF. So yeah, that's an important point to think about. In the definition of PRF, the challenger flips a bit B. And based on that, the challenger decides whether to answer the queries using PRF or RF. After that point, there are many queries, polynomial number of queries, but all of them are either answered using PRF or RFs. The same thing, right? If B was 0, all of them would be answered using PRF. If B was 1, all of them would be answered using RF.
Okay,
Even
so
then,
we
you
won't.
cannot guess the bit B.
Okay. So we won't sample B for each query. Okay.
Yeah, the challenger samples B once.
Okay.
And
Sorry, I mistook that.
this directly comes from the definition of PRF.
Okay, thank you, sir. Thank you.
Yeah, in the definition of PRF, there's a single B. You keep making multiple queries, polynomial number of queries, and then you just have to guess this single bit B. So this seems like an easy job, but even this B is not guessable except with probability close to half. Okay, any other questions? Okay, so now, yeah, so the next hybrid is H2. In H2, we get rid of this random function business entirely. So in H2, we output Ri and M0I XOR some random number, completely random number Ri. Okay, and again, Ri and capital Ri, they are both sampled uniformly, either from M1 or M2, just appropriate length. Okay. So now note that a random function did not always give you a completely random output. Because if you query the same index twice, even in a random function, you get back the same value. Here, even if this little ri's are the same for two different messages, capital Ri's might still be different. So that's the only slight definition. Okay. So what I will claim is that H1 is actually identical to H2, conditioned on the event that Ri and Rj are different if I and j are different. So if there are no collisions in picking Ri, then basically these two hybrids are essentially identical. Okay, but then you note that probability of a collision is negligible. Probability that some Ri equals some Rj such that they are picked at random is is exactly equal to 1 by 2 to the power the length of these strings, which is M1, I guess. Okay, so you can take a union bound. But there are only a polynomial number of these strings. So probability of any collision happening, collision happens with negligible probability. And then finally, we'll have our hybrid 3, where we can just replace this value with completely uniform value. So the same thing, except that now this is just, actually, let me just, why not change the message just like last time? So this is now M1I XOR RI. Because RI is now completely uniform. And we will be able to claim that H2 equals H3. And again, you do the same hybrids in the reverse order, and finally, you get to the same distribution, except you have been able to switch the message. Okay, and I wanted to spend some time on the general techniques for constructing hybrid arguments a little bit before this class ends. So, you can look at the details in the notes. So any questions? So now this is very nice, right? So we were able to construct a PRF from any PRG, and then given a PRF, we can sort of construct almost a dream version of encryption schemes. Key can be small, you can encrypt very large messages, you can use the key any polynomial number of times and so on, which is, of course, what we want in practice. Right? So now let me take the remaining 10 to 15 minutes of the class to talk about hybrid arguments in general and common mistakes while talking about hybrid arguments and so on. So it will just be a bunch of questions, which I hope that you will be able to answer for me. Okay, so we'll have fun with hybrids. So suppose we have a student, let's say Bob, who is enrolled in our class, and Bob submits the first homework, and Bob makes various type of arguments, and hopefully you will try to tell me if these arguments are good or bad. Okay, so let's say we start with this distribution K comma M0 concatenation K, where K is sampled from so this is the ciphertext and the key concatenated with each other. Okay, K is sampled at uniform, and let's say Bob writes that by the security of the encryption scheme, this is computationally indistinguishable from when we are encrypting M1. So is this correct or is there a problem here? I'm starting with a very simple question. So note that this distribution consists of the ciphertext and the key concatenated with each other. Okay, so looks good to one student.
Well, you could decrypt it and then you could get back the message.
Yeah, so clearly if somebody gives me either this distribution or this distribution, I have the key, I can just I can just decrypt and recover the message, right? And then clearly these two distributions are not computationally indistinguishable. So what went wrong? So I'm looking for a more precise answer. So clearly, the statement is wrong, but the hybrid argument, it seems like it was done correctly. So what is going on? M0 and M1 are recoverable constants that identify the distribution. Oh, well, that was the case even if key was not present.
I guess just the hybrid argument assumes that the key is unknown, essentially what we're making.
Yeah, that is a good point. So that is essentially what it boils down to. So note that, do I have the definition of encryption? I think I raised it. Okay, so note that security of the encryption schemes, they rely on the key being chosen uniformly at random, right? And then adversary only gets to see the ciphertext. And then we have a guarantee that any PPT adversary cannot tell apart the ciphertext for M0 from ciphertext for M1. Okay, so only in these conditions the security of encryption holds. So to invoke security of encryption, key must be uniform to the adversary. Okay, if you indeed generate the key and just give it to the adversary, it was generated uniformly, but it is no longer uniform to the adversary. Okay, what do I mean when I say key must be uniform to the adversary? It means that adversary can't tell apart a random number and the key. Okay, and as long as this condition is satisfied, you can invoke the hybrid argument. But here, because you just put key as part of the output which the adversary sees, key is no longer uniform to the adversary, and hence this hybrid argument is wrong, right? Let's go to another hybrid argument. So I will encrypt the same message twice. M0 concatenation K2 M0 such that K1 and K2 are both generated properly. And Bob writes that this is computationally indistinguishable from the same distribution, except that you are encrypting M1. Is this correct or wrong? And feel free to take a guess. No points for getting the answer correct or wrong. We are just trying to have fun. Okay, one student is guessing that this is wrong. Any other thoughts?
Hey to me.
Okay, another guess is correct.
I don't think it's correct. The hybrid argument won't go through.
Okay, so we have another wrong, and in the chat another one correct. So we have 2 versus 2. Any other guesses? Okay, another one for correct. So we are leaning towards correct now. Okay, yeah, so this is actually correct. This is because the security of the encryption scheme does not rely on the message being private. It only relies on the key being sampled uniformly. Okay. You can actually try to prove this using a hybrid argument, a more detailed hybrid argument. So what I can try to do is I can write encryption of K1, comma M1 and encryption of K2 with M0. So I have 2 ciphertexts. I switched M1 first. So I can claim that these 2 guys are computationally indistinguishable. And why is that? Because even in the security of encryption, adversaries even given both messages, M0 and M1. They are not supposed to be private or anything like that. Even you are completely given M0 and M1, and it's still, I can swap M0 and M1 in the ciphertext, and still the adversary cannot tell the difference. Okay, so one way of viewing encryption is that as long as you guarantee the encryption scheme that key is chosen in a nice, correct way, it will guarantee the moon for you as far as message is concerned. Right? You can encrypt the same message multiple times. And oh, and by the way, I forgot. Sorry. Only if encryption is multi-message secure. Right? And in fact, multi-message secure. Oh, no, sorry, I made a mistake. You don't need multi-message security here because these 2 keys are different, uniform. So this holds for every encryption scheme. If this key K1 and K2 was the same, then you would need multi-message security here. So these kind of things are very important to keep in mind. So does this make sense, or? So let's go to the third exercise. Third one is essentially the same as the second one, except that we put the same key in both places.
Sorry, could you talk again why, if it were the same key, it would need multi-message security?
Yeah, so if it is the same, so that's my third example, right? So yeah, we will discuss that. So if your key is the same, then with the same key, you are encrypting twice, right? So this almost follows from the definition of multi-message security that you encrypt. Here, your vectors can be seen as M0, M0 versus your another vector is M1 and M1. Okay, and multi-message security basically says that this is a vector of length 2, even if you have an arbitrarily long vector of any polynomial length. Multi-message security says that given all these ciphertexts versus these ciphertexts, they look computationally indistinguishable. So we are planning to add these examples to the notes. They don't exist in the notes right now, but hopefully by the end of this week, we will have updated notes with these examples and details of why it does or doesn't work. Yeah, did you have a question?
Yes, yes. So, sir, for 3, you said you need multi-message security. But if you are encrypting the same message, like M0 and M0 with K1 and K1, and on the other side M1 and M1 with like a different key, like like the same key, why do you need multi-message security? Like multi-message security was required when you had M0 and M1 M2, right? Like because if I have M1 M2 then and M0 then I can say that my first and second half are same, so I can easily tell one and the other apart, because M1 and M2 will never go to the same ciphertext. But if you are encrypting only M1 M1 and M0 then I think you don't need multi-message, right?
So I think you're thinking about the counter example. So the same counter example, you're right, it doesn't apply when I have M0 M0 and M1 M1, right?
Right.
So it is possible that even single key security might be fine in this example,
Because
but it
like,
may not be.
Because what I'll do is that if you have an adversary for even for single message, I'll just like what I'll do is so I can construct an adversary when you are encrypting it only once, which is like you can easily generate a counter example when you are encrypting it only once, because what you can do is you will give me 2 encrypted messages, I'll just concatenate them again. Like if you give me 2 messages, I'll just concatenate them and send it to the adversary that can distinguish the 3 parts. And then this will be a like adversary for the that distinguishes the single encryption scheme. So
okay, so let me say, yeah, I understand. Let me say a little bit more here. Think about a one-time randomized encryption scheme. So in that case, if you encrypt the same message twice, maybe this encryption scheme becomes completely insecure. Because if it is randomized, you will get 2 different ciphertexts here. And maybe you put these 2 ciphertexts together, you can recover some information about the message directly. So, but if you use, let's say, one-time pad or any deterministic or stateless, then you are right that you cannot tell apart these 2. So maybe this was not such a good example. But in general, if you are reusing your key, you are encrypting multiple messages with your key. To talk about any kind of security, you do need multi-message security. I am sure that you can construct one-time secure randomized encryption schemes, which will actually allow you to distinguish these 2 messages. Okay, let me move on to the sort of the last example which I was thinking about. So now what you do is I have a randomized encryption scheme and I use the same I use the same randomness multiple times. So I encrypt a message, let's say M0 with randomness R. And then I encrypt another message with the same randomness R. Now I would like to claim that M0 prime and M1 prime, that I can change the message vector. And by the way, encryption has multi-message security. So yeah, what do we think about this? So this is probably the most tricky. So recall that in the definition of encryption and how the encryption algorithm is defined, you are supposed to generate R at random. Okay, so this turns out to be also wrong. Okay, because the security of the encryption scheme relies on R being uniform, right? And if you are reusing R, then this guarantee goes out of the window. If you are doing any funny business with R so that R may no longer be uniform, then yeah, we cannot rely on anything. So there's a question, why is R being passed as an argument to encryption? So you don't need to pass it. This just denotes that there are two encryption algorithms, and they use, for whatever reason, they end up using the same randomness R. So security of encryption relies on, number one, key uniform. Number two, randomness, as the name says, uniform. Any reuse or disclosure of even a part of these things will require new proofs or new security arguments. Maybe it still works, maybe it doesn't, but at least the standard definition says nothing in that case. Okay, and we have already seen that. For example, if somebody was reusing the key, one-time pad became insecure. But then, we explicitly were able to construct new encryption schemes where key reuse was fine. Okay, so with multi-message encryption schemes, maybe key reuse is fine, but still randomness reuse, I don't know. Never talked about that. Maybe you can construct a new type of encryption schemes which even allow for randomness reuse. But at least standard security guarantees goes out of the window. Okay, and by the way, let me contrast this with one-way functions. In one-way functions, the security relied on only the input being uniform. Okay, so in one-way functions, suppose the input is not being chosen uniformly, then maybe one-way functions can be invertible. Or maybe if the adversary is given, some fraction of the input, maybe one-way functions can be invertible. So that's why it's very important to look at security definitions and sort of hard code in your brain what the security relies on. And you have to pay special attention to things that are uniform. So this is probably the most important. Things that are uniform, it means that adversary really must have no idea about that. And only then the security holds, otherwise basically the whole thing might just go out of the window. Okay, any questions before we stop? Okay, so we will stop and we'll put out the notes for this part soon.